Xing Fan.
Okay, can you hear me? Okay. Thank you for inviting me here. I'm gonna talk about the singlet in a penny trap universe. I use this word just because it's ITAMP workshop. There is a subtitle Laboratory Cosmology. Yes. Did not? I shared. Can you see it? I shared. Ready. This one.
You hit share screen, right?
Yeah.
On that, right? Behind that one.
I think I shared.
I'm signing off as shared also. I feel like it.
Okay. Maybe it's not. Yeah, but yeah, feel free to interrupt me. If there's any.
You're shared.
Okay.
Oh, there's the
Conservation. Okay. Okay. But yeah. So single electron in a penny trap. But what I'm gonna talk about is really our recent result. This new measurement of the electron's magnetic moment. And I can't overemphasize the contribution from Jerry Gabriel, who was the group lead, PI of this project. And at that time, I was only just a PhD student. But this result was actually already 1.5 years ago. And I also gave more than 20 talks everywhere. And if you haven't heard, please invite me. And I'm also joining Harvard Physics Department from next year, July. So I decided to talk about something new, okay? So, whenever you talk about something new ideas, there is always, risk of competition and being stolen. But I thought it's a good chance to, show new proposals and get feedback and maybe criticism from this wonderful ITAMP participants. Okay, so let's start physics. What is electron's magnetic dipole moment? Eric already gave a really great introduction, but let's start from a classical picture. So suppose you have an electron, orbiting electron like this with an angular momentum L. This electron has a negative charge, right? So this orbiting motion is a current loop which produces a magnetic field along this vertical direction. And the produced magnetic moment is given by this simple expression. E is the charge of electron, m is the mass, and L is this angular momentum. And we know that electron has a spin angular momentum given by h bar divided by 2. So a naive guess is there must be a magnetic dipole moment from spin. So you plug in this number into here. So you make a guess. The spin magnetic dipole moment must be this expression. However, whenever physicists use a question mark, the answer is no. There is a correction factor G here. That's how you define a G factor. And this G factor is about 2 plus correction from higher order QST calculations. And this is the most precise prediction from the standard model calculation. That's what we want to measure and test the standard model. So here I show the standard model calculation. Again, it's a magnetic moment. So interaction of electron with a magnetic field. So electron comes in here, magnetic field, and something happens here. You can calculate from the first order 3 level, 1 loop level, 2 loop levels, and you need up to 5 loop levels to predict at 13 or 14 digits. And what standard model gives you is the G factor as a function of a fine structure constant. So the calculation gives you these coefficients in front of this fine structure constant. And this fine structure constant is something you have to measure independently, like in Saida's talk using rubidium or cesium in Fogel-Miller group. Then here is the current situation. So there are 2 independent standard models, 2 independent alpha measurements. Those are 2 values here. And these 2 are so theoretical prediction. This is a previous G factor measurement in 2008, and this is our recent new measurement of G factor. We reduced uncertainty by about a factor 2.2, and there is slight discrepancy between both of them. So here is a standard model calculation diagram. And I have no idea why I'm showing here, but it looks difficult, right? And when I saw these diagrams, which one do you think is the easiest or hardest? Let's say which one is the easiest? Maybe this 1A, or I thought this B, this one must be the easiest one, but they told me this is actually the hardest one to calculate. And I always just show this to overwhelm you. So this is what they are doing. This is their language. They have more than 13,000 diagrams to predict G factor. Anyway, let's go to the experiment. I'm an experimentalist, so this is easier to understand. You just apply magnetic field. So this principle here shows how you measure G factor. You apply magnetic field, put one electron in this magnetic field, measure energy difference between spin up state and spin down state. The energy difference is given by this expression, and from the definition, G factor appears here. The leftmost term here is the spin precession energy in this magnetic field, and the rightmost term here, this is the Planck constant times ED over M. So this is actually the cyclotron motion's energy in the same magnetic field. So if you want to determine this G factor, you measure two frequencies, spin frequencies and cyclotron frequency in the same magnetic field. And by dividing them, you get G factor. Ideally, you want to do this in a free space. However, it's difficult to confine electron in a real free space. So we use an ion trap called a penning trap. Penning trap is a charged ion trap using a combination of static magnetic field and static electric field. By applying magnetic field in this vertical direction, this gives you a cyclotron motion around this axis, which gives you a radial confinement. And the cyclotron motion is pretty fast, about 150 gigahertz for our typical 5 Tesla magnetic field. So now this electron is radially confined, but about this, how about this vertical motion? So to confine this vertical motion, we use electric field. The picture here, the figure here shows the 2D schematics of the trap. You have top end cap and the bottom end cap. They are grounded, and you have a ring electrode at the center. So it's 3D trap, 2 end caps and 1 ring electrode. By biasing the ring electrode positively, you can trap this electron vertically using electric field. This oscillation is much slower, about 100 megahertz level, like RF range. And in actual, the trap looks like this. Magnetic field applied in the vertical direction, and the top end cap here, bottom end cap here, and the ring is this center electrode here. And the electron is trapped in the center volume here. So we measure two frequencies, spin frequency and cyclotron frequency, and determine G factor. So there were many talks about EDM. What's the big difference between measuring EDM and magnetic dipole moment? One of the biggest difference is this electron G factor is a non-zero measurement. What does this mean? I'm gonna give you a quiz. So I'm gonna show you a box with many balls there. So please count how many balls there. 10 seconds, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many? 37. 40. So this is a 2.5% precision measurement. Okay. And measuring zero means is there any ball in this box? Okay. So I'm not saying which is easier. I'm just saying they are, essentially different. They are essentially two different measurements. And so G factor, basically standard model calculation predicts the density of the ball. And the spin frequency is like the box size. And the cyclotron frequency is the box size. And number of spheres here is the spin frequency. So by measuring, box size and number of spheres, you can calculate the density, which is a prediction from the standard model. Okay, so we learned penning trap and we learned measuring something finite. But how do we, detect electron from a penning trap? You can trap, but you have to see some signals, right? We observe electron using the image charge. So here is again penning trap, electron oscillating up and down, axial oscillation. And the electron has a negative charge, so there is an induced image charge on top and bottom end cap. This image charge moving from top to bottom, bottom to top, which gives you an oscillating current through this resistor. By reading out the voltage drop through this resistor, you see a sinusoidal oscillation. And if you take a Fourier transformation, you see a peak. So this is like what appears on spectrum analyzer. You see a peak that corresponds to the axial oscillation frequency. And what we can do is, for example, if we monitor the peak power of this on this spectrum analyzer and slowly fire electron gun into the trap, you see a step increase from empty trap, 1 electron loaded, 2 electrons, 3 electrons, 4 electrons. So we can non-destructively detect the motion, and count the number of electrons in the penny trap using this method. By the way, the induced current here corresponds to about 10 femtoamp for 1 electron. That's our signal. So this was about axial motion, but what we really want to know is the spin frequency and the cyclotron frequency. How do we control or measure them? To do that, we actually have to use quantum mechanics. So as I listed here, quantum cyclotron motion. Cyclotron motion is 150 gigahertz for 5 Tesla field, which corresponds to about 7 Kelvin equivalent motional temperature. And we cool the trap much below this temperature to about 100 millikelvin. So actually, this classical orbiting picture is wrong. You have to use quantum mechanics to describe this motion. What does this mean? So in the penny trap, what is the quantum state of electron? If you put electron, 1 electron in a trap, it has either spin down state or spin up state. And each of them can actually have a quantized cyclotron levels. So quantum cyclotron ground state, first excited state, second excited state, and so on. So this is a quantized version of radial harmonic oscillator. And the transition frequency here corresponds to the cyclotron frequency, of course. For example, if electron is here at the beginning, you can drive this transition using a microwave drive. The decay rate is about 5 seconds. This is radiative synchrotron decay. Experimentally, we measure this transition, anomaly transition, which is the spin frequency minus cyclotron frequency. So this is actually in the RF range, about 170 megahertz. You can drive this transition like this. Oh, sorry, animation crazy, but this electron also decays like this. So that's how we manipulate quantum cyclotron state and the spin state in the penny trap. So this is how we manipulate, but again, yes, it's beautiful. You can in principle do this, but how do you read out this transition? To read out this transition, we need another method. We use a quantum non-domination readout. This is actually similar to like an NQR resonance or electron shelving readout in atomic physics. The principle is, again, you have electron oscillating up and down. And this axial frequency, we can detect directly from the image charge that I just shown. And then we add a nickel bottle, so we call magnetic bottle around the center of the trap. This distorts the homogeneous magnetic field a little and creates this V2 times V square gradient, quadratic gradient. V is this vertical direction. So then the potential along this z-axis is given by the sum of electric field potential plus magnetic field potential. Some of them you may be familiar with, like low field seeker, high field seeker state. So those the magnetic dipole moment of electron couples to the field gradient and creates modifies the spring constant along this vertical direction. So for example, for n cyclotron ground state and first excited state, they have a different axial potential. And experimentally, what you can see is if you monitor, this frequency from this axial frequency, when you have a transition, the axial frequency shifts a little like this. And this shift here is proportional to the artificially induced magnetic field gradient. We can see this clearly. So this is a demonstration of a quantum cyclotron motion. Y-axis is the actual frequency shift. X-axis is the time, and you can see discrete jump from ground state, first excited state, and second excited state. So with all those principles, here is the apparatus. Penning trap is actually pretty small, still larger than the ion trap, I think. But the penning trap electrode itself is about 5 centimeter. You can put on your hand. And the penning trap is housed in a titanium vacuum chamber, which is connected to a dilution refrigerator from top through this top plate. So this setup comes to the bottom here. And here is our dilution refrigerator. And we have another superconducting niobium titanium solenoid at the bottom of a liquid helium dewar. And this dewar has a cover on top. So we open the cover and insert this DR from top. And that's how we form a penning trap at the bottom here. So with this principle, you do spectroscopy. What you measure is these two transitions. So spectroscopy means you apply drive and measure at what frequency transition happens most frequently. So two graphs here, excitation probability as a function of gravity tuning for cyclotron transition and anomaly transition. Anomaly is this spin flip transition. This anomaly transition is pretty narrow. We are pretty happy with this line shape, but the cyclotron transition was was broader, and it's actually asymmetric. And this was actually one of the systematic errors on our head. This was caused by the axial motion temperature. So we still have finite axial motion of electron in the trap, which couples to the magnetic field inhomogeneity in the trap. So we need a better axial cooling to narrow this cyclotron line shape. So you might say, this is such an easy measurement. You just measure two frequencies and you get PRL. This is such an easy measurement. However, that's of course not the end of the story. There is a really huge systematic shift called cyclotron image charge shift. What is this? Basically, here is again penning trap, and as soon as you put electron in this penning trap, this electron, does cyclotron motion like this. So here is the top view of this. Imagine you cut this penning trap and look from top. Electron doing cyclotron motion. However, this wall is a conductive wall, so you have an image charge from this cyclotron motion as well. And this image charge distorts the electric field inside because, of course, this has a positive charge, right? The thing is, the diameter of the trap is about 6 millimeter. And if you divide this 6 millimeter by the speed of light, it's about 0.02 nanosecond. That's the required time for the signal to propagate from the center to the wall and propagate back to the center. So this is comparable to the cyclotron frequency, this oscillation frequency. So there is actually a phase delay between this electron's motion and the effect from the image charge. Okay, and what's worse is, for example, when this condition is satisfied, they will be 180 degree completely out of phase. Okay, and wait a second, what is this condition here? Cyclotron frequency equal to speed of light divided by the size times some integer. This is actually the resonance condition of this penning trap. Okay, so this is actually a cavity QED effect, coupling of electron cyclotron motion to this penning trap microwave cavity. So it's a really non-linear shift and strongly depends on the electron cyclotron frequency. So to correct this, we have to measure this penning trap cylindrical trap resonance really well. To do that, we measure the de-excitation rate from this n equal 1 to 0 as a function of cyclotron frequency. So in this measurement, we sweep the magnetic field. And you see many peaks that correspond to the well-known cyclotron cavities resonance. From the electric field distribution, we know these two modes couple to electron really strongly. So when we measure G factor, let's say if you measure G factor at 4 points here, before applying this image charge correction, they line up inconsistently like this. And after applying correction, they line up more consistently like this. However, notice that the scale here, this is 10 to the minus 12, and we are measuring G factor. We want to measure G factor at 13 digits level. So for example, this point, the correction here is 30 times larger than our final uncertainty. It's a really important and a huge systematic shift. So to do that, to really make sure we are doing this correctly, we measure G factor at 11 different fields from about 3 Tesla to 5.5 Tesla. And the white points here are before this image charge correction. And after applying this image charge correction, they line up almost more or less consistently. And from the reduced chi-square and p-value, we think we did this correctly. And by averaging all data, we report the final G factor value. And if you trust the standard model calculation, this is also a new report of a fine structure constant. By the way, this was the hardest part in this measurement. You recharge and change the magnetic field 11 times to really study the systematic effect. So this was about the reported measurement. What's next? How can we improve more? One thing is, as I said, the line width of this cyclotron transition, this is dominated by the axial motion of electron in the trap. And actually, we can do resolve the sideband cooling using microwave, even for electron in the pinning trap. Electron doesn't have optical transition, but you can use microwave to do sideband cooling. So axial quantum number is about 30, cyclotron is 0, and by coupling them, you can cool this axial quantum number to 0. And this could be also useful for quantum computing using electron in a penny trap. Some people are trying to do this. And if you make this table here shows the first trapping and first ground state cooling for ions and electrons. So ions, of course, have been achieved by more than 30 years ago, but electron ground state cooling has never been achieved. So if we manage to do this, this is beneficial for G factor measurement. And also about this systematic effect, this cavity resonance image charge effect. As I said, it depends on the cavities, the spinning trap geometry resonance really significantly. So we are thinking of moving from this cylindrical trap to spherical trap. Okay, probably we are the only person interested in spherical trap in the world. But because this spherical trap has a higher symmetry, the resonant mode inside is actually cleaner. So the graph here shows the expected or calculated image charge shift as a function of cyclotron frequency for our current cylindrical trap and spherical trap. So for our last measurement, we had to measure like 50 to 70 microwave modes to apply correction properly. And for the spherical trap, we only have to measure hopefully 1, 2, and maybe one more here, 3 modes, which should reduce this systematic effect significantly. You can compare this idea with the history of ion clock, for example. So whenever you change the trap shape, you make improvement in the precision. And for electron spinning trap, that's also true. From the 1987 hyperbolic trap, we changed it to a cylindrical trap, and now I'm proposing to change to spherical trap. Demonstration, I think we can do within 1 year, and achieving this precision takes more, let's say 5 years. And honestly, we need one more new idea to make another breakthrough. And then one more idea to reduce this broadening, let's say inhomogeneity of the inhomogeneity in the magnetic field. Special relativity quantum non-dimension detection. I introduced this method using magnetic field inhomogeneity to do quantum non-dimension measurement. However, of course, this induces very strong magnetic inhomogeneity, which is why we saw a broad cyclotron shape. We can actually remove this photo completely and shift to a completely magnetism-free trap. But then the question is, how do you read out cyclotron transition or spin transition from the trap? So when you have transition, let's say cyclotron transition from ground state to the excited state, from the special relativity, this electron gained some energy given by this quantity. And because then now the electron here in this state is a little heavier, right? Because of this cyclotron transition. So the axial oscillation frequency in this direction actually decrease a little because this axial oscillation is a function of the mass as well. So by improving our detector, we should be able to see the mass increase of the electron by single quantum transition in the next generation pinning trap. So the signal will be, again, a shift of axial frequency, but the shift will be much smaller than our current shift. So we need a better detector, which is we are planning to use a squid detector, actually developed in my PhD work. And by combining them, we can address some from physics, I think interesting physics. One is, as I mentioned before, muon G-2 discrepancy. So Fermi-Lab reported, together with theory calculation, of course, reported discrepancy. And if it's a new real physics, you should be able to scale this muon G-2 discrepancy to electron G-2 by the square of mass ratio. So if I take the muon G-2 experiment value minus theory value and scale by the square of mass ratio, you achieve this expected discrepancy in electron G factor. And if we manage to improve what I proposed, what we just proposed, you should be able to see muon discrepancy with about 2 sigma confidence level. And of course, we need another improved alpha determination, improved and consistent alpha determination as well. Then all these techniques should be also useful for action search as well. So single electron in the pinning trap is actually a really good photon counter, mid-electron bolt photon counter. So it's actually possible to search for action or dark photon by just leaving one electron in a pinning trap and wait for the transition from the ground state to the first excited state driven by action or whatever exotic force. If you calculate transition dipole moment, this transition is about 550 dBi, pretty large for atomic physics field, and it's background free, and transition is mid-electron volt range, and this system is magnetic field compatible. And we already demonstrated this idea in this paper. So it seems to me this is a very good detector to search for QCD action. And one more thing we can do is with the same technique, we can measure positron G factor. Now this is a lepton CPT test. If we manage to measure this will be the most precise lepton CPT test. And by using a similar technique, by using a similar technique, we can measure the mass ratio of positron and electron at a pretty good precision. Should be 10,000 times better than before. And now this is a mass measurement, and it's actually sensitive to anti-gravity at a few % level as well. So with all these techniques, here I show a slide with with a lot of information, but yeah, many ideas, and I think there are a lot of physics we can probe by improving the technique further. What I didn't mention is, for example, the limit from King prop usually also contains this electron G factor limit, so we should be able to improve this as well. Then I want to mention another activity using pinning trap that I'm involved. Neptune project, nuclear electroweak measurement in pinning trap using near degenerate energy state of molecules. Whatever, but what that means is we can trap molecular ion in a pinning trap and measure the parity violation effect in the pinning trap. Here are our beautiful apparatus like the pinning trap, lasers, ion source, shim coils, and field stability, and so on. So here are the people. This is led by Donald Garcia Lewis at MIT, and Jonas Carlsen recently got position at Texas A&M. So we are now working on 29 SIO plus for proof of principle. And at this Texas A&M, you have access to radioactive molecules from the Cyclotron Institute. So we hope we cover broad range of molecules. So then at last, I'm also involved in the Electron EDM collaboration. John Boyle and Dave DeMille will give a talk tomorrow, so I will let them talk about this. And based on my experience in EDM and molecular EDM and cryogenic ion trap, we are now trying to measure this nuclear shift moment of thorium-237 F class. The idea is as introduced by Nick. By combining molecule with octapole deformed nuclear, we can get a huge enhancement. And we can improve the current limit, for example, on theta QCD, just with one molecular ion and 1 day of measurement. So here is a very simplified schematics. You have to produce pH-237 F plus, and you have to do measurement. And you need some buffer gas or whatever cooling scheme here to actually bridge this creation process to the measurement scale. I think this is actually a general statement. You need some kind of bridge from nuclear energy scale, typically 10 keV, 100 keV, to what we want to do in AMO physics scale, less than milli-electron volt. So this is just one idea, and we are also exploring other ideas to bridge these two really different energy scales. So here I show a plot of probed energy scale as a function of ER. With thorium-237, let's say with these assumed parameters, I think we can reach here with a real more challenging parameters here. And the good thing of ions, or let's say ion trap, is you don't need so many numbers, and as long as ions you can trap. So maybe in the future some other more rare isotopes, maybe we can apply techniques to them as well. So that's all my talk. I talked about electron magnetic dipole moment, briefly electron EDM and nuclear EDM. This is an ion trap, spinning trap, and a hole trap. And this is molecule. And by combining them, I hope we can do some fun stuff. Thank you very much.
Great, thank you. Questions for?
I can also project. So you mentioned you're looking to improve the sensitivity of the electron magnetic dipole by a factor of 10.
Mm-hmm.
Do you know what sort of particles and loops in the standard model you would start being sensitive to? Will you start being limited by this QCD background?
Yeah, well? QCD, we will probe. That's one thing, and actually probably important for muon G-2 people. Then we can probe QCD contribution kind of in a really clean and a different system. Then it's another way to measure QCD contribution to muon G-2. And I'm also personally interested in lepton CPT test with positrons. And what I didn't mention here is actually by measuring the G factor of electron, you can probe the substructure of electron, whether electron is really a fundamental particle. Like proton has a G factor about 5.5 because proton has quarks inside. So by improving the precision of G factor, we can probe those smaller scale of electrons. That's kind of my personal interest.
But at some point, it becomes hard to know when you're measuring the substructure of new physics versus just
yeah, exactly. QCD, right? Yes. At some point, you have to care QCD and what I show here, contribution from weak bosons, and also 6th order QED calculation. That's I think about 100,000 diagrams. 10 times or more than 6th order.
So again, the day, it doesn't matter how large your systematic errors are, but how large are the uncertainties in your corrections?
Yes. Yes.
And I can imagine that it's harder to manufacture a spherical trap than a cylindrical trap.
Mm-hmm.
And you might have a cleaner looking spectrum, but a more uncertain spectrum.
Okay. Very good question. So that's probably true, but that's actually also already true in cylindrical trap. So from each let's say, a cylindrical trap from each resonance, you can recalculate, for example, the trap geometry, right? And that's actually already inconsistent depending on which mode you use. They never line up perfectly. So what we always have to measure the resonance frequency by ourselves in situ and correct anyways. And the advantage of a spherical trap is you have fewer resonance, but also there are many more resonance, but don't contribute to the first order. So if you have, let's say, even some imperfection, let's say in the geometry here, if you have imperfection, for example, in the cylindrical trap like this, then that will shift this, for example, this resonance directly to left or right. But if you have imperfection here, that will show up as the first order small perturbation in this big curve here. But in some sense, this geometry is already suppressing improving the tolerance to imperfection by one order. That's kind of my argument.
Question first for the axion detection.
Uh-huh.
You mentioned you could reach the QC axion. What kind of interaction strength do you expect?
Oh, okay. I didn't explain so much, but the idea is you actually cannot reach QC action by just putting one electron. You need an external focusing antenna outside to correct all axion converted photons from this external antenna to here. So in axion field, it's called dish antenna. But basically, you can look at this as a sensor and another much larger axion converter outside to forecast the signal from the larger surface area to the small surface area here. Am I answering your question?
Yeah, yes, well, it's very interesting. But then what are the numbers to expect? Do you think that will be bounce better?
Oh, so for like in terms of hardware, we are assuming about 2 meter scale external antenna. But honestly, 2 meter scale and with also some enhancement scheme that hasn't been demonstrated. So we can search for QC action probably at one narrow frequency, but covering the media control broadly will require another breakthrough. That's my honest opinion.
So in those traps, out of curiosity, patch contact potentials are always subdominant
Oh.
mechanical kind of tolerance.
It is. I wouldn't say not dominant. I would say correctable. The thing is, if you have a patch potential or imperfection of the voltage on one electrode, that actually shifts electron from the center to some offset place, and that actually creates coupling to higher order microwave. Yes, you see some peaks that shouldn't appear if electron is exactly at the center. But we can still measure them and
the patches don't move with time.
it's really hard. Honest answer is I don't know. Yeah, I don't know honestly.
Yeah, so also on this, so it sounds like the entire work is reduced to systematic effects.
Yes.
Okay, so so there's no, doesn't really help you get better detection scheme.
It probably, of course, helps at some point, but currently it's systematic error dominated. For example, in the last measurement, statistical sensitivity probably only 3 days, 4 days data, but it took really, 9 months, 10 months to collect all these data and apply correction properly. It's completely systematic error dominated.
And to actually speed that part, there's no other way to.
Yeah, so the thing is, this is an image charge effect. So as soon as you have a trap electrode, you have this image charge. Maybe we can somehow, optically trap electron. I don't know. That's what I wrote here. We need one more breakthrough to break this uncertainty. This is really a realistic uncertainty that I estimate based on spherical trap. And if we want to improve another factor 3, for example, I think we need a really new idea.
Can the theoretical calculation also improve by
Oh yes, they are working on this. But honestly, they are already much better. Their calculation uncertainty is already about I think about 1.5 times 10 to minus 14, and G factor precision is completely limited by the fine structure constant information. So calculation it is necessary, but at this point, the experiment side, both us and the fine structure constant, are the limitation.
Can you play some sort of games with skin depth where you have a DC trap for your penny trap, but somehow the microwaves go
Yeah,
through?
I thought about maybe like a ITO coded trap, something like that. You know, DC trap, but microwave the transparent
Electric, yeah, something like
trap.
that.
So I think that's worth exploring. I don't know if ITO is transparent or not at mid-electron low, but that's one approach, I think.
let's think all those features.
Yeah, I don't think there's anything official after this. Just don't get into too much trouble.